Hello and welcome to our tutorial series about line differential protection. Line current differential protection is a core principle for overhead line or cable protection and is applied from transmission down to distribution voltage levels. Our tutorial series should give you an introduction and deep insights into line differential protection theory and the CPROTEC 5 line protection devices. This session is about line differential protection basics. If you already joined one of our last energy automation webinars, you already know the Q&A field in the upper right corner of this application. Please enter your questions there. We will collect them and answer them in the live Q&A session for those who attended the tutorial series. My name is Philipp Stachel and I'm the product manager for CPROTEC 5 line differential protection devices. This is the agenda for this first session. First, we will have a look at the line differential protection principle and the commonly applied characteristics. Afterwards, we will shortly look into multi-ended line differential applications. In the third part of this session, you will learn about Siemens CPROTEC 5 line differential protection devices. Here I will present you the data alignment, the stabilization methods, and the protection stages in the CPROTEC 5 devices. The line differential protection principle is very old. It started around 1900 with patents by Shugart. A balanced beam was used for the DC differential protection. Later, around 1900, Shugart enhanced it further for the AC lines, but still used the local measured currents for the differential protection. Merz and Price in 1904 marked with their patent the birth of the line differential protection. Some extracts of this patent are shown on this slide here. The currents of both sides of the line are summed up electrical and transferred using a pilot wire to the remote end. In case a differential current is flowing on the pilot wire, it operated the circuit breaker. This principle was then applied in electromechanical relays from about 1910. In these relays, the mechanical torque produced by the differential current operated a trip contact. Around 1960, analog electronic circuits replaced the balanced beam systems and a higher sensitivity was obtained. Unfortunately, in these devices, the long-term stability of the used component was not very good. So from 1997, digital protection relays were introduced and replaced the existing mechanical and the analog electronic relays. They used the existing pilot wires, but later introduced also other types of digital communication. Okay. Let's come to the line differential protection principle. The line differential protection principle provides the following advantages. It only requires CTs. There's no need for a voltage transformer. It's a unit protection, so 100% of the line is protected without an additional need for a time delay. Therefore, it's suitable for short cables or overhead lines. It's also possible to use it for multi-ended lines, so tapped lines, and also applications with a transformer in the protected zone, or for series compensated lines. There is no impact for parallel line switching states or power swings. All kind of network grounding can be considered. It's very sensitive for high resistive or arcing faults. And finally, the relay settings are quite simple. On the other side, there are also some disadvantages to mention. First of all, you need a communication channel for this protection principle, which needs to be fast, reliable, and it should be possible to supervise this communication channel. The line differential protection is a unit protection. That means also that it does not provide a backup protection for external equipment like following lines or transformers. Only the equipment in the zone which is delimited by the location of the current transformers, is protected. The protected zone is shown in below figure here, in the green color. There we have two power grids, A and B, which are connected by a line. The current transformer locations delimit the protected zone, and that gives you 100% of selectivity. The measured line currents are evaluated in the connected line differential protection devices, which are here marked with the 87L, which is an ANSI code. And the line differential protection principle is based on a comparison of the local phase and the remote phase currents. It applies the first Kirchhoff's law, which is a current law, which says that the sum which flows into a node always equals to 0. The fundamental frequency component is evaluated, which is obtained using Fourier filters. But there are also other methods on the market. The current measurement is normally defined towards the protected object, which is shown in the figure with the arrows pointing towards the protected object or into the line. There is no need for an operational time delay, so an instantaneous operation is obtained by this protection principle. But you need a communication link between the relays, which I already mentioned, which needs to be secure and safe. Let's have a look what happens if we have a current flowing at the line. In the first example, we have the normal load condition, which is a load current flowing at the ideal line, shown here. And we look at the phasor diagram on the top right, with the imaginary part and the real part of the phasors, which are measured by the protection relays. No? The current IA is measured by the relay in A, and the current IB is a current measured in the relay B. This is of the opposite direction because the load flows is through the line. The current phasor is therefore in the opposite direction. Most relays in the market will calculate the differential current as the sum of the current phasors from n terminals. For our two-ended application, the differential current is therefore IA plus IB and then the absolute value. This is the ideal condition. In reality, the CTs will have some small errors, which will result in error in the amplitude and the phase, which is shown in the figure here with some small circles on the top of these phasors. The differential current as the sum of both current phasors will result in a very small differential current. This small differential current needs to be considered in the relay settings. This is particularly the case if you have an external fault situation. The measured currents at the line terminals are the through fault currents. The higher currents result in bigger CT errors and therefore a higher differential current. For this reason, we need a minimum pickup threshold for the differential current setting. In extreme situation, one CT could saturate and the apparent differential becomes very big. For this, we need other types of stabilization, which I will present later to you. For the internal fault condition, the phasor measured at the terminals A and B appear in the same direction on the complex plane. The sum of both phasors will result in a very big differential current. Here we also consider some CT errors, which are expressed by the circles at the top of these phasors. For the internal fault condition, these errors are not so important as the differential current amplitude is very high, and the relay will typically operate and trip the circuit breaker. Up to now, we only looked at ideal lines. For a real line, we will have some line impedance, ZL, but also line capacitances to ground and between the phase conductors. This is a P model of a line, of a real line. Consider we have a load current situation with the current IA and the voltage UA at the terminal A, which are more or less in phase. That means that the cosinus phi, so the power factor, is close to 1. The capacitive current, IC, is added to the current IA and forms the line current. We ignore the voltage drop of the line impedance and can add at the terminal B another portion of the capacitive current IC and get to the current IB in the opposite direction. The sum of both current phasors result in a differential current IDIF. This will result in quite a significant differential current, which is the charging current of the line. This needs to be considered for the relay setting. The minimum differential current pickup threshold must be set higher than this expected charging current. Many relays in the market also provide a capacitive charging current compensation. This requires a local measured voltage and will subtract the calculated charging current. The relay becomes more sensitive to low fault currents, but also requires a reliable voltage signal. A very common stabilization for the line differential protection is a so-called dual slope characteristic, which is shown on the top right figure here. As explained before, the minimum pickup threshold IDIF greater will consider and stabilize for the capacitive charging currents. The first slope, M1, will stabilize for small CT errors up to the highest expected load currents of the line. The second slope, M2, will stabilize for higher CT errors due to starting nonlinearities of the CTs. The restraining current is calculated as the sum of the absolute current value scaled by a vendor-specific scalar value K. For example, K equals 1/2 is a typical value. A differential current seen above the characteristic will trip the circuit breaker, and below the characteristic the relay will stabilize and be stable. The CPROTEC 7SD series, so the CPROTEC 4 and CPROTEC 5 series, use a different restraining current calculation, shown here, which takes into account the CT errors already. The adaptive restrained current calculation considered also the effects of a signal distortion and time differences in the communication channel. I will explain this a bit later. Therefore, the stabilization characteristic looks different and is a single slope of 45 degrees, so M equals 1. We provide a setting for the minimum differential pickup current. This should set higher than the expected capacitive charging currents. A differential current above the characteristic will trip the circuit breaker, or the relay will trip the circuit breaker, and below the characteristic the relay will stabilize. Instead of comparing current phasors with amplitude and phase, it is also possible to differentiate between an internal or an external fault by analyzing the phase information only. This is done in the phase comparison principle. For completeness, I will give you a few information on this principle, which is applied in the CPROTEC 7SD80 devices for phase currents. only the polarity of the currents are exchanged between the local and the remote terminal. The lower bandwidth requirements allow also that a power line communication system can be applied for this protection principle. The current amplitude is evaluated only for a release threshold. Therefore, some information is lost, and this principle is less sensitive and accurate than a current differential protection. In this example here, we consider an external fault condition. If the measured current is positive, we transmit a signal to the remote end, which is here called mark. Otherwise, no information is sent. Space. This is done at both terminals. The local binary sequence of marks and spaces is combined with the received binary information, as shown here. The combined binary signal only contains marks for the external fault, and this does not lead to a trip condition. Small gaps due to phase errors must be tolerated and stabilized by some settings. In the legacy technology, information compression was used. The phase comparison is done for each phase current in the 7ST80 device. Legacy relays further compressed the information and evaluated only one combined current signal. This could be, for example, a negative sequence current. For the internal fault condition, the currents at the line terminal A and B are more or less in phase, so both relays see the fault in the forward direction. The combined binary signal with local and remote current polarities result in a sequence of marks and spaces, shown here. This will result in a trip condition. If we plot the operating characteristic of the phase comparison relay with regards to the differential phase angle, we get the following two-sector diagram on the right-hand side. If the phase difference is about 180 degrees, the relay will stabilize. The tolerance angle, which is shown here with phi z, can be expressed also by a setting or by a counter. Other region, the other sector, the relay will trip the circuit breaker. Not shown in this diagram is the effect of the minimum release current, which would result in a circular area around the origin which would be stabilized. An enhanced phase comparison principle, which also considers the current amplitudes, is the so-called alpha plane characteristic. In addition to the evaluation of the phase difference, the ratio of the local and remote current amplitudes is made. Phase currents and/or negative sequence and/or zero sequence phasors are evaluated. For load or external fault conditions, both current magnitudes are similar in their value. The ratio is close to 1. This will result in a circle. Some current amplitude difference shall be acceptable. Therefore, we set a maximum ratio R in this D-rays. This defines an inner and an outer radius of this stabilization area. The maximum phase angle is defined by the phase error to be considered, similar to the previous explained phase comparison principle. Also, the alpha plane needs some additional stabilization for CT saturation, which is not shown here. In the next part, we will look at the special applications with more than 2 line terminals. Such a multi-ended line differential application could be required in case of tapped overhead lines. Distributed energy resources like wind or photovoltaic parks are often connected to existing overhead lines nearby. Also, smaller rural load centers are connected by tapping the line. The pickup differential current setting must be increased to stabilize for these generation or load currents. This will reduce the sensitivity for high resistive or arcing faults at the main line, especially for high load situations where we have a high restraining current. Applications using distance protection are even more difficult to set in such applications and are not a good alternative. For applications with higher load centers or bigger DER connected to the line, it is recommended to build a new substation, of course, or to use the multi-ended line differential protection scheme. In such a scheme, the currents of more than 2 line terminals are compared and needs to be transferred between the differential protection relays. We can consider communication channels in a ring, a chain, or as a star. First, look at the chain or ring topology. The devices in such an arrangement needs to be identified clearly using IDs. Here we use the labels 1, 2, 3, 4. In a ring topology, each device requires 2 protection interfaces to their neighbor. For Z-Protect devices, in a ring topology, the channel between relay 1 and 2 will be the hot standby path. That's why it's dashed here. The relay 2 will send its local measured phasor ID to the relay 3. The relay 3 then adds up its local measured current and sends it to the relay 4 plus the received current from the relay 2 ID. So ID plus IC is transferred to the relay 4. The relay 4 does the same. The same applies also for the opposite direction, where the relay 1 sends to 4, 4 to 3, 3 to 2. That means the relays in the middle are the first relays which are able to calculate the differential current because they get it from both sides. This principle is used in the Z-Protect 4 and Z-Protect 5 series. In a star communication topology, the currents from all terminals are transmitted to a master device. This one here. The device requires more communication interfaces, while the slave devices only require one communication interface. It's a centralized protection principle, as the current can be only evaluated by the master. The trip signal needs to be transferred to all the other relays. A redundancy concept is required for the scheme because if you fail this relay, then the whole scheme would fail. A decentralized scheme can be obtained if all the relays at all the terminals have all the information, have connections to all other line ends. Due to the higher amount of required communication interfaces, this is often only applied up to 3 line terminals. Let's have a look at the Z-Protect 5 line differential protection. In this graph, I tried to place the different Z-Protect devices regarding their hardware, IOs, and modules over the functionality for the applications. At the lower end, you will find the Z-Protect 4 compact device 7SD80 and the Z-Protect device 7SD610. The Z-Protect 7SD5 provides more IOs, but can be also used for multi-ended line differential protection and optional backup distance protection. The discontinuation of Z-Protect 7SD610 and 7SD5 was recently announced. Therefore, these devices are not recommended for new applications. For new applications, I recommend using the CProtect 5 series here. Starting with the non-modular device 7SD82 without and the 7SL82 with a distance protection. The 7SX82 is a universal protection device which provides even more functions. The modular devices like the 7SD86 and 7SL86 provide a 3-pole tripping, while the 87 devices also include single and 3-pole circuit breaker operation. The highest flexibility is provided by the universal device 7SX85, which also includes the line differential protection principle. The table shown in this slide shows a detailed comparison of the mentioned devices. I will not go through all the details, but it's important to mention that the CProtect 5 series devices are compatible with the CProtect 4 devices 7SD5 and 7SD610. The phase comparison principle in the 7SD80 is something special and is only provided in this device. So there's no compatibility. Different types of communication interfaces are provided, listed here. From direct fiber optic, pilot wire communication, IEEE C3794, up to the recently introduced line differential over IP Ethernet networks. For details, please also attend the dedicated session for the line differential protection communication in this tutorial series. With CProtect 5 7SD8, you get a multi-ended line differential protection device for applications up to 6 line ends. Also, a transformer can be in the protected zone. The device provides a charge and current compensation and binary user data exchange, including remote tripping. Several protection communication interface options are available, including a direct fiber connection for long distances up to 100 km. There are also interfaces available to connect to existing wide area communication networks via multiplexers using optical interfaces like IEEE C3794 or electrical interfaces like E1 or T1 using communication converter. Recently, we introduced a direct interface over IP Ethernet networks. If you are interested in this, I recommend you the dedicated tutorial session. The line differential provides also test features where you can test local, the loopback, and also the full characteristic. For the IEC 61850 sampled values coming from a merging unit or a test set, we are able to handle the test flag according to the standard. On the right-hand side, you see the structure in Dixie 5. The line differential protection is grouped inside the function group line with all its function extensions and the protection stages. The interconnection of the protection stages is shown in this logic overview. The core protection stages, which are the EDIF and the EDIF fast. The EDIF is a more sensitive but slightly slower than the EDIF fast 2. For compatibility with CProtect 4, we also provide the EDIF fast. The difference between both stages is explained a bit later. For special applications, we also provide an earth or zero sequence and a negative sequence current differential stage, INDIF and I2DIF. Both are intended to be more sensitive than the EDIF. Already mentioned, additional features like the in-zone transformer protection and capacitive charging, current compensation, and supervision functions are included. In general, the current phasors are estimated from sampled current waveform using FIR filters. The sample time and data window must not be equal at the line ends. So the sampling runs independent and asynchronous in the devices. This is also the case if an external synchronization is applied using a 1 pulse per second signal or a precision time protocol or 1588. These asynchronous phasors then need to be aligned in the devices before the Kirchhoff's current law can be applied. For each protection interface, we measure the round-trip delay time between the relays and also the device time offset, DTO. I will shortly explain what that means. The drift in the device time offset is also measured. This means that we also calculate the difference of the used crystal oscillators of the main CPU, which gives you a microsecond accuracy. In case of communication channel rerouting in switched networks, a transient asymmetry can occur. This is detected automatically and compensated for a given duration. In case you have a redundant communication interface, the device selects the one which is synchronized and has a higher bandwidth. For example, if you use a direct fiber optic channel and also a 64 kilobit channel, and both are synchronized, then the direct optical fiber is selected. Let's have a closer look at the data alignment for current differential protection. Consider a waveform in the time domain as shown in this figure. As mentioned, the sampling of the current waveform occurs asynchronous in both relays A and B. The time-based counters run independent and are derived from the CPU crystal frequency. The data window with 20 samples used to estimate the current phasors are not exactly at the same time. We have a difference in the sampling time in both relays, which is here marked with the delta T window. This difference needs to be eliminated, so a synchronization is required. There are two common synchronization methods used in the market. First is the so-called ping-pong method, which requires no external synchronization and only a small bandwidth. I will explain this in the next slide. The other method uses a global time reference as an external synchronization, like the 1 pulse per second derived from a global navigation satellite system, GPS or Galileo, or a precision time protocol, PTP or 1588. Let's have a look at the ping-pong method. The protection communication data is sent by telegrams between the relays. These are these blue and the red boxes. This occurs every 5 or 10 milliseconds, depending on the bandwidth of the communication channel. From time to time, a synchronization telegram is also exchanged. The synchronization is based on the timestamp, including in these telegrams. With the knowledge of the local timestamp sending a message and the local timestamp receiving a message, and also the information of the processing delay in the remote and relay, we can calculate the average transmission delay of the communication path, dt. Assumption for the ping-pong method is always that a symmetrical communication channel is used. Using two data tuples allows the calculation of the device time offset. Also, the drift in the device time offset can be estimated and results in a microsecond accuracy. The channel delay and the device time offset are supervised. the transmission delay is calculated by the difference between the sent and the received telegrams. Jumps in the transmission delay may occur, for example, if you have a symmetrical channel switching in the network. This is detected and compensated. The algorithm can handle up to 155 milliseconds of transmission delay. But this is more a theoretical value. Normally you will tolerate only a few milliseconds or 10 milliseconds of transmission delay. Otherwise, the communication channel might not be suitable for this protection principle. The device time offset, DTO, as a difference of the time-based counters, is supervised also. Normally, we don't expect a jump in the device time offset because it's derived from the CPU frequencies. And any jump in the device time offset is assumed as an asymmetric channel delay. An alarm will be raised if such a jump occurs. If the jump remains longer than 5 seconds, the relay will block until a manual interaction. So it's in lockout condition. This shall prevent a maloperation due to a permanent channel asymmetry. There's a user setting for the maximum tolerated channel asymmetry, which goes into the restraining current component, which I will explain a bit later. Now let's come to the line differential protection stabilization methods. Now we will have a closer look at these components. The differential current calculation is standard and is shown here only for completeness. The restraining current per phase is calculated from the sum over all line ends for the maximum phase CT error and the signal distortion, plus a user settable threshold for the minimum pickup and the assumed maximum channel asymmetry. The idea behind is to stabilize the differential protection as much as needed and not so static like for the dual slope characteristic. Maybe this is the biggest differentiation between these principles. First, we will have a look at the stabilization component, which is derived from the CT errors. On the left-hand side, the transfer characteristic of a real CT is shown. This is a blue curve. The secondary current is drawn as a function over the primary current. An ideal CT would transform the primary current until infinity. Now this is not the case because the real CT will saturate or will have some kind of saturation. So it will have some nonlinear effects. The difference between the ideal CT and the real CT is a measure of the error. In the linear range, where we also find our load current, the error is very small, but increases slightly when we get closer to the ratio where to the currents where we have CT saturation starting. This is defined by international standards as the factor KSSC or the accuracy limiting factor. For example, a CT of class 5P10 will have a 5% error at 10 times rated current and rated burden. On the right-hand side, the characteristic of two CTs is shown. CTA, CTB. The CTs are slightly different in their linear range. You see a difference in the slope. And also the saturation starts earlier in the CT and the side B compared to the side A. For the same primary current, we measure and calculate a differential current. It's the red curve. In the linear range, the error is very small. But with the starting of the saturation, the error increases significantly and will saturate if both CTs are in the saturated area. How does the adaptive algorithm compensate for these CT errors? The restraining current component for the CT errors shall only stabilize for errors in the linear range. So in this area here. Differential currents caused by CT saturation will be stabilized by another method, which I will explain a bit later. A two-slope characteristic, I zoomed in, two-slope characteristic is used to approximate the CT error in the linear range. Up to a settable changeover value, K changeover, the factor CT error A and CT error B are used for the compensation. For the changeover ratio, I recommend a setting of 1.5 times the rated line current. This provides a higher sensitivity for load currents and a higher stabilization for fault currents. The factors for the CT error A and B are a recommendation from Siemens based on the normative CT errors for the different CT classes. In the relay manual, you will find this table. For the CPROTEC 5 to CPROTEC 5 communication. For different current transformer classes, 5P, 10P, TPX, and so on, IEC and ANSI types, the recommended settings for the CT error A and B are provided by this table. With such a stabilization, it is also possible to use different CT classes at the line terminals. For example, you could use a closed iron core CT, like the 5P, the class 5P, at one terminal, and a CT with an air gap, like the class TPY or TPZ, at the other terminal. Due to the different transient behavior, I would not recommend such combinations, or would only recommend it for special application. It's always best practice to use the same CT types at the terminals. The second restraining current component is for signal distortions. Signal distortions could occur due to CT saturation, but also for higher current harmonics, for example, for inrush currents. In below figure shows the measured secondary current signal with a significant CT saturation. And due to the saturation, the fundamental current component will be smaller and the differential current will be present. This needs to be stabilized. The difference between the measured signal red, the red curve, and the fundamental current component, which is the blue curve, is indicated, and the quantity for the adaptive stabilization is highlighted with the green area. If there is not enough fundamental current in the signal, the differential protection is blocked. The third restraining current component is derived from the synchronization mismatch. Just after the synchronization of the protection interface, this component tends to higher stabilization. After a few 100 milliseconds, the steady state is reached, where we mainly stabilize for asymmetrical transmission delays. That means a difference in transmission delays in sending and receiving direction. Such a difference in sending and receiving direction could occur in applications using switched telecommunication networks like SDH or MPLS. Let's look at the example. For example, we consider a channel delay from the relay A to B to be 4 milliseconds. On the return path, B to A, we have a 3 milliseconds delay. The ping-pong method applied in both relays calculates an average channel delay TD of 3.5 milliseconds. This results in a synchronization error of 0.5 milliseconds, which is a phase error of 9 degrees at a 50 Hz system. The apparent differential current seen by both relays is proportional to the load current or the measured current amplitude, but also depending on the phase component. The expected channel asymmetry in your switched network can be provided by your telecommunication team or expert. This value which they give you shall be set for the expected difference in the sending and receiving channel asymmetry. For direct fiber optic connections, we recommend to set this value to 0 milliseconds. But for IEEE C3794, we recommend to set it to at least 0.3 milliseconds up to 0.6 milliseconds if you have a weaker communication system. The last part of this presentation is about CPROTEC 5 line differential protection stages. First, look at the logic diagram for the core protection stage EDIF. As already presented, the EDIF stage works with the full cycle current phasors. The differential current as well as the restraining current are calculated and evaluated. Two settable thresholds are provided to also cover the switch on to fault conditions or the line energization. Current jump detection is intended and provided to allow a faster operation of this stage after the fault inception. As mentioned previously, a faster charge-based differential stage is available also. This is called the EDIF Fast and the EDIF Fast 2 stage. This is based on a charge principle. So the charge is calculated from the current samples every 5 milliseconds, running with the same differential protection algorithm, but the window is shorter. It's only a 5 millisecond data window. The stage is only active for high fault currents or for high currents, which allows a faster tripping compared to the EDIF stage. The differential charge is calculated at all the line ends and compared in a similar way as the differential current. Here you see cut of the waveform and the different 5 milliseconds window. Each of these window has a 2.5 milliseconds window offset. The instantaneous tripping of the stage is sufficient. For special applications, we introduced in the version 980 also a time delay setting with very short times. How does the stages EDIF and EDIF Fast work together in parallel? Consider the following fault inception waveform. The EDIF and the EDIF Fast are calculated every 5 milliseconds. For the EDIF is used a 20 milliseconds window, while for the EDIF Fast only a 5 millisecond window is evaluated for the charge, and this is for the current phasors. When we have a fault inception during such a calculation window, this will impact our calculated phasors. So that means if we have detected fault inception, the IDIF, so the differential current calculation gets blocked, and these windows then are marked as invalid. In this case, the EDIF Fast will be available and will operate very fast for these faults just after the fault inception. Due to a possibility of a DC component in the signal, and also the possibility of current saturation. The either fast windows are marked and blocked 2 to 3 windows after the fault inception. A limitation of the either fast stage and the motivation for the new either fast 2 stage shall be presented in the slide here. The problem is as follows. The CT saturation can result in conditions where the differential current during the internal fault is smaller than for an external fault. Look at this example. We have an external fault where the fault is fed from the right-hand side, so the relay at the side A saturates very heavily, while the relay at B does not saturate. So this gives you a very high differential current, which could be significant. For the internal fault condition, you can consider that the fault is fed only from the side where we have the relay A and no network at relay B. So we see it's this heavily saturated fault current at the relay A, which gives you, compared with the relay and B, a very small differential current. So for high fault currents with saturation, this can result in a blocking of the EDIF fast stage, because there's not sufficient current to enable this stage. The EDIF fast stage could not be fast enough for all the applications. The improved EDIF fast 2 works together with the saturation detection. The advantage in CPROTEC 5 are that you still have the EDIF stage, there's no change. We also provide the EDIF fast stage, which is still available for a compatibility to the existing CPROTEC 4 devices. And new improved is the EDIF fast 2 stage, which includes a saturation detector. How does the EDIF fast stage works when the saturation is detected? It blocks when the saturation is detected for external faults only, and does not block for internal faults. If the fault changes from an external to an internal condition, these faults are cleared faster. So it's in general a better response for high fault currents. For special applications, we introduced from the version 930 a more sensitive earth or zero sequence current differential stage. Consider the following network, where we have a high load on the line, which also results in a high retaining current in the both relays. So this gives you a reduced sensitivity for high impedance faults at the line. For such special applications, we recommend to use the IN-diff or the I2-diff for this protection of this line. And that's it for the first session. Thank you for attending this first session of our tutorial series for line differential protection. This session was about the basic principles and key features of CPROTEC 5 line differential devices. We recommend you to also attend the other sessions, which will focus on the setting examples in Dixie 5 and provide deep insights into protection communication interfaces and even more details. Please also check the internet to watch past webinars or subscribe for a training. See you soon.